Welcome back to CS 520. In this session I'm going to talk about implementing threads on the Intel 64. So the goal here is to provide the illusion of multiple threads executing when there's really only a single processor. And we have two very simple primitives. One called thread create allows me to create a thread. The thread has a work function that takes a void star, and that parameter is the second parameter to thread create. So I create a thread, I pass it a function for the work to be done by the thread, and I can pass it an argument for the work function as the second argument to thread create. Again, modeled on POSIX threads. Thread create returns a long, which serves as a thread ID to identify that thread. I also have a second primitive called thread yield. So in this library, the user has to explicitly call thread yield in order to hand control from one thread to another. So when a thread calls thread yield, it's willing to give up the CPU and let another thread run. At the very end of this session, I'll talk about how to hide that function from the user. But for the initial discussion, we're going to have the programmer explicitly calling thread yield to hand control from one thread to another. One thread will yield control of the processor to another one. So what do we have to save for a thread when we go to shut it down, when it calls yield and it wants to allow another thread to run? We want to put this thread to make it idle for a little bit. Well, what is the state of a thread? What is a thread really? Well, a thread, I would say, is the program counter, which tells us where the thread is executing in the code, the other registers that it may be using to store intermediate results, and then most importantly perhaps the stack where its function call frames are stored. So if we could take a snapshot of that information and keep that from the moment the thread yields to the moment it's woken up later, that will allow us to bring a thread back to life at the same point it was when it called yield. Where are we going to put this information? Well, we're going to keep something called the thread control block, or I'll refer to it by TCB. This data structure will contain a thread state when it is not running, and we'll keep a list of TCBs for ready to run threads. This list I'll refer to as the ready list. So all TCBs on that list are threads that are ready to run, and thread yield will just move through that list. My convention is that the head of the ready list is the current running thread. Okay? So this thread control block would be a struct in C with a pointer to chain to the next struct in the list. Okay? So let's think about thread yield. When thread yield's called, we'll rotate the TCBs on the ready list. The first one becomes the last, so the current running thread moves to the end of the ready list. The second one on the list becomes the first, and that thread, the TCB for that thread, will be the next one to run. Then we'll save state of the running thread into its TCB, and we'll restore the state of the next thread from its TCB. Sounds simple enough. But of course there's going to have to be some magic here, because how do we get one thread to hand over control to another thread? Well, the key is that we're going to change stacks. One of the registers that we'll save in the TCB is the stack pointer. When you restore the stack pointer of the next thread, that's the magic moment when you change from running on one stack to running on the second stack. And that's really when you change control from the first thread to the second thread. And again, by manipulating the stack pointer, we can make this magic happen, which I think is incredibly cool. You may disagree, but you're just going to have to put up with me for the rest of this session. Slight complication when we start up. We can create TCBs for threads that we get a chance to create, right? So a user calls thread create, we can create a TCB for the new thread, but we don't create the main thread. The main thread is just up and running, but yet we're going to want to allow it to yield, so we need it to have a TCB where we can save its state. So the trick here is that the first time a thread primitive is called, we'll create a TCB for the main thread and make it the sole node on the ready list. So in our implementation, we'll have some kind of global static. That's just a flag that tells us whether we've initialized the system yet. And when one of our primitives is called, we'll check that global static. And if it's not set, then we know, okay, we need to create a TCB for main. And in fact, we need to initialize the ready list to simply contain only that TCB. Okay, so we can get a little bit of initialization we have to do, and we won't be able to do it until the first time one of our functions is called. Okay, let's think about saving and restoring the thread state. Well, we need to access registers, right? We need to save the program counter, we need to save the stack pointer, we need to save other registers. So that means we're going to need to have code in assembly language to access those registers. So I'm envisioning having a function written in assembly language, which I'm calling ASM yield. It takes two parameters: the current running thread's TCB and the TCB of the thread that's going to run next. And which registers exactly do we need to save? We actually only need to save the RSP and then the callee saved registers, RBX, R12 through R15. We don't explicitly save the frame pointer or the instruction pointer because they're going to be in the stack, as we'll see in a second. So by saving the stack pointer, we'll implicitly be saving the frame pointer and the instruction pointer. Okay. Now it turns out the TCB will also contain slots for RDI and RSI, and this is part of the strategy for starting a newly created thread. And we'll talk about that in a minute as well. But first, let's look at how we're going to access the TCB from assembly language. Again, the TCB will be a struct at the C level, and we just need to think about what that struct will look like from the point of view of the assembly language. So the struct, if the TCB contains these registers and maybe some other control fields that I'm not going to talk about in this session, the main thing I'm looking at today is these registers. And we just need to think about how the C compiler will lay out memory for those. And everything on the Intel 64 is a quad word here. These are all 64-bit register values, so they're all going to take up 8 bytes in memory. So we just need to keep a mapping from the logical register and its position. In other words, its offset from the front of the struct. Now, a second ago I mentioned that I'm envisioning this routine, this ASM yield routine, which is going to do this save and this restore of the state as having two parameters, right? One is the current TCB and one is the next TCB. And we know that those parameters, the C compiler will generate code so that the first parameter will be an RDI, the second parameter will be an RSI. So when we're writing the assembly language, we know we're going to have a register pointing to the base of the struct, to the base of the TCB. So it's pretty easy then to write code to, for instance, save R12, right? Move quad word R12 into 32 off of the RDI, right? 32 is the slot where I've decided to put R12. And I just have to make sure that the offsets here correspond to my C struct declaration for the TCB. When I go to restore, I'll have RSI pointing to the new thread's TCB, where I want to restore from. But the code is, of course, very similar. I'm going to be moving 32 off of RSI to restore R12 for the thread that's going to run next. Okay. So, the low-level stuff here to save and restore state is in assembly language, and of course, before I call that code, I'll do everything I can in the C code. So thread yield, the C code for thread yield will manipulate and rotate the TCBs on the ready list. And only when it's time to save and restore the state will it call the assembly language routine. This assembly language routine is going to restore the stack pointer, so you've got to call it last. You've got to do everything in C first, and the last thing in thread yield, the ccump function, will be the call to ASM yield, the assembly language function. All right, let's take a look at the Blackmagic now. And let's think first, what are the stacks going to look like? All right, the stack for the current thread is on the left here. Okay, the stack for the thread that's going to run next is on the right. And let's think about it. The thread that wants to yield would have called thread yield, so there'll be a frame created on top of the stack for thread yield. It's going to do everything it can in C code, which basically boils down to just rotating the TCBs on the ready list. And then it's going to call ASM yield. And again, a stack frame will be created for ASM yield. Right, an ASM yield, because it's a good Intel function, the first thing it'll do is it'll push the RBP and it will move quad word RSP to RBP. So the picture looks like this, right? When thread yield called ASM yield, the RIP at that time gets saved. And then the first instruction in ASM yield will push its frame pointer here, okay, and establish a new frame pointer. So we'll have RSP pointing to the top of stack like always, and RBP also pointing to the top of stack. Okay. Well, if you think about the old stack, the stack of the thread it's going to run next is going to look exactly the same because it's shut down in the same way, right? It called thread yield, and thread yield called ASM yield. It has an RIP and an RBP on top of the stack. Okay. So what we really want to do, the magic here, is that if the stack pointer is pointing here, we just want to rotate it around so it points over here. Okay. So ASMU, when it restores the stack pointer, that's what it's going to do, right? It's going to take the stack pointer from pointing here and rotate it around to point here. And then the magic happens, right? The magic happens because we do the move quad word to restore the stack pointer, and then we do a pop quad word, right? The next thing here is the pop quad word to restore the frame pointer, but now we're on the other stack, so we're restoring the frame pointer of the thread that's supposed to wake up, and then the return instruction will restore the instruction pointer for the thread, and we're up and running in the new thread. So that's the magic moment, right? When we change that stack, we restore the stack pointer from the next thread's TCB, the stack pointer rotates around here, and then these instructions here, the pop quadrant and return, are really executed by, I would say, conceptually anyways, by the next thread, right? That thread is up and running. It does a pop quad off its stack and a return, and it's back in the code wherever it was, okay, which actually would be the thread yield call. But the thread yield call will do a return, and then it will be back into the user's code at the point right after it called thread yield. So that's the magic. If you think about it in some sense, one thread calls the top of ASM yield, and the thread to run next executes the bottom of it. Okay, and that's the Blackmagic, but it's really not magic at all, right? It's just a matter of manipulating the stack pointer to switch from one stack to the other. Okay. Well, there's only one thing wrong with that, which is we have a start initialization problem. How do we get a thread running the first time? You know, there's going to be one time when we're going to yield to a thread when it didn't go to sleep with thread yield. Rather, it hasn't run before, right? It's the first time we're yielding to it. So we have to have some more kind of tricky maneuvers at the point that we create a thread to get this to all work. So again, thread create is our primitive. It takes a work function and a parameter to be passed to the work function. And what do we want thread create to do? We want to create a TCB for it and put it on the end of the ready list. That's just the semantics that we have. It's when a new thread comes in, it goes to the end of the ready list. I have to wait its turn to run. Okay, we're going to use malloc to allocate a stack for it. Right, we need to have some memory set aside for its stack. And we're going to save the base of the stack in the TCB so it can be freed later. And I'll talk about this with a diagram in just a second, but you know, when this thread shuts down, we're going to want to free up that allocated stack. So we're going to need to remember where the base of the stack is. And then we're going to initialize a TCB in the stack so that the thread will execute this function. And this is the trickery, right? This is the trickery. What's going to happen is the thread is going to run. It's not going to run the work function immediately. Rather, it's going to run a little function that we're going to write and include in our code. And it's only 1, 2, 3, 4, 5 lines of C. And there it is, right? Again, it takes the work function and the info, that pointer to be passed to the work function as its 2 arguments. So it looks a little bit like thread create. But the body of the function says, okay, call the user's work function with the parameter. All right, so that's the deal, right? We're going to do their work. But the reason we're introducing thread start is because we have to get in after that work function gets done, and we have to clean up and destroy this thread. Okay, so we're going to slip a call in here called thread cleanup, and that's why we don't execute the work function directly. Right? We want to execute the user's work function and then get a chance to clean up to get rid of the thread. Okay, so thread create has got to get things going so that it's got to initialize things so that the thread will start executing this thread start function. Okay, again, I'll have a diagram and try to illustrate that in a second. Let's just think about that thread create return value. We need to return some kind of thread ID so that's unique to the thread. So one way to do that is just to use the address of its TCB. We know that will be unique for the thread. We can use that as the thread ID. So we'll return that out of thread create. All right, let's take a close look at this initialization problem we have. Okay, we're going to again, a little bit tricky here, but I'm going to draw the diagram in my usual fashion, right? The high memory is down at the bottom of the page, low memory is at the top. So when I malloc the stack in thread create, I'm going to get a pointer here to the low address, right? That's what we expect malloc to do. Give us the low address, and the object that we just allocated extends into higher memory. Okay, but we know that stacks on the Intel hardware grow from high memory down to low memory. So we know we're going to want to initialize the stack. So the stack pointer's up here and the stack will grow down this way. So one of the things we've got to maneuver around is that we're going to get an address here, but we're going to want to go manipulate the high end of that, the high address into that block of memory. Okay, but we can do that because we know the length. Obviously, we told malloc how many bytes we want. We told it how many quad words we want, essentially. So we can manipulate this as perhaps as an array and get down here to the end of the array and fill in values in order to get things started. And here's the trickery. The trickery is I want to put the address of the thread start function. Again, it's a function that I write. It's in my code in the thread library. I want to put the address of that function in a slot at the high end of the malloc block. Okay, and the way I've done it here is I actually have 2 words where it doesn't really matter what are in them. I'll try to explain what's going on as we go through this, but these X's are we just allocate space and we just leave it there. So in the very last word in the malloc block, I'm going to just put 0, let's say. Then I'm going to put the address of the thread start right below that, and then another garbage word here. And in the TCB for this new thread, I'm going to save the address of that -3 slot. It's going to be what I put into my RSB slot in the new TCB. So when the thread wakes up, that's its stack pointer when it wakes up the first time. And in fact, let's think about it. Let's go over here to ASM yield again. Again, the magic moment here, we change the stack pointer and then we run the pop quad word. So this garbage word will be on top of the stack. It's going to be placed into RBP. Okay, and then we do a return. The return takes the address of thread start and puts it into the instruction pointer. Okay, so thread start now starts executing. And at that moment in time, after the return, my stack looks like this, right? I just have the garbage word that was in the -1 slot, and the stack pointer is pointing to that. So that's what things look like after I do these 2 instructions. Okay, and that's again after ASM yield has its magic moment, and we switch stacks so that this is now the stack for the CPU is using. Okay, it does a pop quad word to put something into the frame pointer, and it does a return, which puts this thread start address into the instruction pointer, leaving the stack looking like this. And thread start, like all good Intel functions, is going to do this push quad word of the frame pointer. Okay, so this garbage word that was popped off by the pop quad word RBB is going to be pushed back onto the stack. Okay, and then we're going to do move quad word RSP to RBP to set up a new frame pointer. So when I get done with these two instructions, I've got a frame pointer pointing here, and I've got those two garbage words that were in -1 and -3 originally. Okay, and what's going on with these words is, if you think about it, the frame pointer always points to the save frame pointer. So that garbage word is just a sort of a faux frame pointer, as if there was another frame underneath me, but I don't have another frame underneath me. And the same thing, this is sort of a faux instruction pointer, as if somebody called me, right? So those garbage words don't really matter because they're never going to be used. But I'm just establishing a frame on which I can do stuff in the future. I can grow in the future after the user code starts running. Okay. And the reason why these garbage words don't matter is because we're never going to return, right? When a thread terminates the work function, we're going to call a thread cleanup, and it's just going to kill the thread. So the stuff will never be used on the bottom of the stack. Okay. Now there's one other trick, is that thread start takes two parameters. It takes the work function and the parameter for the work function. So we have to manipulate, again, the new TCB so that we put those values, right? Thread create was passed a value to be used as the work function. It was passed a value to serve as the argument to the work function. So in thread create, we need to put the work function in RDI, and the RDI slot in the TCB, and the RSI slot for the info pointer, so that when the thread wakes up, we'll restore RDI and RSI, and from the point of view of thread start, it will look like those parameters are sitting there. So it gets the work function, so everything will work, right? Let me just flip back to the earlier slide in case I've lost you here. Thread start, again, is going to execute this, right? Work info and thread cleanup. In order to do this call, the C compiler is going to generate code for this, but it's going to assume that the first parameter is an RDI, the second parameter is RSI. So that's why we have an RDI and RSI slot in our TCB, so that we can initialize RDI and RSI so that they will contain those two values, so that when thread start is woken up by this trickery here, RDI will contain the work function and RSI will contain the parameter to be passed to the work function, thus allowing the generated code here, the assembly language code generated by the C compiler, to just magically work. Okay, so pretty tricky stuff here. It all relies on us understanding the conventions for how parameters are passed and how frames are created and so forth. Okay. Alright, so I hope you had your blood sugar at a high level when you sat down to watch this, because that stuff is pretty tricky that we just went through. Let's finish it up. Let's talk about thread cleanup here. What do we have to do? When thread cleanup is called, it means the work function is finished and we just want to destroy the thread, basically. So we're going to remove the TCB from the front of the list, from the front of the ready list, because that's my convention for running threads. It's going to be on the front of the ready list. We're going to remove the TCB. We're going to free the stack, but it turns out, we got to be careful about that. It's dangerous to free the stack that we are still executing on. So the typical strategy here is to defer the free of that stack by one call to thread cleanup. So we'll have maybe a global variable or something that will keep track of the next stack to be freed. And when we're cleaning up one thread, we're freeing the stack for the last thread we cleaned up. And we're remembering this thread stack in the global variable so that the next time thread cleanup is called, we can free up that stack. So we can solve that danger that we're running on the stack. We don't want to free it, because why is it dangerous? Well, free is going to scribble around on that freed up memory in order to keep its data structures. And we don't want it to destroy anything that we need. Okay. So anyways, we'll remove the TCB, we'll free the stack, we can also free the TCB, and then we need to yield, right? We're dying, somebody else is going to run. So in fact, I'm going to call ASM yield here, passing null now for the first parameter, because I don't need to save my state, right? I'm dying, so I don't need to remember anything about the current running thread. I just need to restore from here. Okay, so if you do it, if you implement it this way, it means you need to be able to put a conditional, an if statement like thing into your assembly language code, which says, if first parameter is null, then we're not saving the state for the current running thread. The alternative is to have two versions of ASM yield, one that takes two parameters and does the conventional saving and restoring, and another one that takes only one parameter and just does the restore. Either way will work. Okay, so a lot of trickery there. You probably need to sit down and think about it. I think it's neat. The question is, do you believe what I've laid out there will actually work? So think about it. One last thing is, I mentioned that we'd like to hide the call to thread yield, and we can do this by preemptive scheduling. We can ask the operating system to generate timer signals at regular intervals. And when the timer signal goes off, we can have a handler ready to go, a handler function that will be called by the signal. And what that handler function will do for us, it will call thread yield. Okay, so in this way, the user doesn't have to call thread yields, and time slicing will be used to share one CPU over a set of threads. Every time the timer signal goes off, we do a thread yield. We make the current running thread give up, go to the end of the ready list, and let the next thread run. Okay. Now this is a little bit tricky, because if the handler goes off, we got to make sure that our data structures are secure, and that we can actually tolerate a call to thread yield at this moment in time. And the tricky part here is we must disable the signal handler at critical points when we're inside the thread library. For instance, when we're creating thread and we're manipulating the ready lists, we don't want that handler to be called, because our data structures are probably broken at that point. We go in there and we try to do something else to the broken data structure, we're going to have trouble. So creating a thread is one example. When a thread is being cleaned up is another example. So the way to handle this is that the handler function will check another static global that tells it whether it should actually call the thread yield or not. And if the flag is set by the thread library indicating that we're at a dangerous point in the code, we don't want thread yield to be called, then the handler will just return, which allows the current running thread to continue running for another time slice. Okay. So that's the last step to make this thread library a little bit more realistic, so the user doesn't have to call thread yield. Okay, let's stop here.